All right, guys. So, how many did you get? 8. Did everybody get 8? So, just curious, how many people did a tree diagram? So you remember you're a little bit. Again, did you have to do a tree diagram? No, you didn't need to. Did people just start writing all the options? Right? Was that okay as well? So did anybody do like the box method? Remember we did some sample spaces using the rectangular box? That one you would have had to use it twice to be able to do it, right? So either way, okay, did you guys all get 8? Okay. All right, so you definitely should have got 8. If I add another pair of shorts and another pair of sandals and another shirt, is this going to be nasty to just draw all the samples out? Yes. Okay, it would be horrible. That is not the point of chapter 11. Okay, so chapter 11 is about figuring out how many arrangements, okay, is the beginning of the chapter, how many different arrangements we can make, whether it be with clothing, lining up people at the fountain, moving letters around, okay? We're going to start with permutations, which is basically arrangements of objects, okay? Then we're going to move on to combinations, right? Not today, okay? But we'll move on to combination, which is a branch of mathematics that deals with groupings, like how many groups of things can we do, okay? So this is not an efficient way of figuring out how many outfits, do we have a name, this person can make with 2 t-shirts, 2 pairs of shorts, and 2 pairs of sandals, right? Because they could make 8 different, okay, outfits if they didn't care about matching certain things together, right, with no restrictions. All right, so is there an easier way to determine the total number of outfits without listing all the possibilities or drawing a tree diagram? Did you guys figure out what you could do to get an 8? Right, times all the things. Exactly. Times all your options of outfits by each other. Because how many choices of shirts do you have? 2. How many choices of shorts do you have? 2. How many choices of sandals do you have? 2. What we just did there, guys, is what we call the fundamental counting principle. Okay? So if I did add a shirt to our options, a pair of sandals to our options, and a pair of shorts to our options, okay, guess what 3 numbers we would times by? It would be 3 times 3 times 3. So it would go from 8 outfits all the way up to 27 outfits. Okay. Do you see how this could, bless you, could get exponentially larger and larger? Okay. So think about how many outfits you have in your closet. A lot, probably. Yep. Oh, of course. Absolutely. Right? So yes, you could. This is the same as 2 to the power of 3. Same thing. Right? So when you have repeating, right, choices, you can write them the 2 different ways. They mean the same thing. Right? So that is what we call the fundamental counting principle. So if one task can be formed in A ways and a second task can be formed in B ways, then the 2 tasks can be performed in A times B ways. So I just showed 2 options there, but could I add another scenario here and do hats included in my outfits? All right, you guys are teenagers like Calvert. No, maybe boys would have some ball caps. Right? Well, exactly. Hoodies would definitely be included. Okay. So, but like I said, it doesn't need to. It could be as many cases as options you have for outfits. Okay. All right. So, what are these questions going to look like in Math 30-1? So, we're going to do some questions today. We're going to see some new notation today. It's going to be kind of fun. And something completely different. We're going to take a brain break from transformations. There's no, this is the only chapter in all of 30-1 that has no transformations in it. Okay, no graphs. So like I said, guys, chapter 11 is the only chapter that has no transformations or graphs in it. But guess what? When we go back to 9 and 10, back to graphs and transformations. There's 11 in total. So we're doing unit 4 now. All right. Logs and exponents. All right, so example 1 says a mathematics 30-1 quiz consists of 5 multiple choice questions. Each question has 4 choices, A, B, C, or D. How many different sets of answers are possible? Right, so if we wanted to know how many ways you could bubble in that bubble sheet without any kind of just randomness, right? 5 questions. Not that you have to do this, but I like doing this. It shows me how many questions are on their test. 5. So how many choices do I have to bubble in for the first one? 4. How many choices do I have to bubble in if I'm completely guessing? 4. How many choices do I have to bubble in for the third question if I'm completely guessing? Right, you see the pattern here? And 4. And what am I doing with those numbers? To see how many possible arrangements of bubbling I could do? I multiply them all together. So again, right, this is the same as 4 to the power of 5. So 4 to the power of 5. Right, so there's 24. So there's 1,024 different ways you could bubble that in. Okay? So not that the Alberta curriculum wants you to deal with probability, that's just the IB curriculum, but could I change this question to what's the probability that you get them all right?
Just by guessing?
Not by guessing, using your guys' knowledge of probability that we did in the IB part. Pardon? Say that again.
Yeah,
What is it divided by 1,000?
Exactly.
but I mean like random.
Oh yeah, it would have to be random. Right, so if you just guessed on every single question, you have 1 in 1,024 chance of getting every single question right, which is, as a percent, 0.0976565% chance of guessing all of them right. Okay. Does that make sense that I took that second one into times by 100? Right, because the first one, 1 divided by 1,024, is the probability, which is always a number between 0 and 1. So taking probability and changing it to percent, I have to times it by 100. And again, 30-1, I'm not asking you to do probability. Okay, regular Alberta curriculum. But that's just kind of neat, because just think, if you guess on a test, right, you might be that lucky one, but it's a very, very minute chance that you can do well just by guessing. Right. That would be scary, though. If you get one wrong. That's 20%. Boom. All right. All right, so let's do a few more. So they're obviously, do you think we're going to get more complicated than that? Yeah, it's 30-1. I'm going to add restrictions to the questions, okay? So here, an online game has asked you to create a password. Does that happen to your lives all the time? You're creating passwords for different things? Yeah. Right? So the password must be 4 characters in length. You may use any lowercase letters and any uppercase letters and any single digit to create your password. So how many passwords are possible if you repeat any character? Okay, so again, how long is this password? 4 characters. So 4 characters. And we can use any uppercase, any lowercase from the alphabet. So you do have to know how many letters are in the alphabet. 26. So if you didn't know that, you know that now. Because I do not, on a quiz, guys, want you to go A, B, C, D, E, F, G, H. So now we all know that there is 26 letters in the alphabet. Remember that. But since we can do uppercase and lowercase, does that double my options? In the, right, so we can do uppercase and lowercase, so that gives me 52 options for just letters. But then I can use also any single digit numbers. So what are my single digit numbers? 0 to 9. So there's 10. So there's 10 options for digits, single digits. And again, 26 options for letters, but like I said, we can do lower and upper. So we have 52 plus 10, which is 62. So it doesn't matter where I start to figure out my password. You just have to start somewhere. And here it does say letters can repeat. And with passwords, can we normally repeat things? Yeah, usually passwords we can. Okay? But they will tell you that restriction. Okay? If you can't repeat, they'll tell you. Okay? So then, if I'm picking this part of my password first, because it doesn't matter on the line where you start. Do you guys agree in this context? Because are we multiplying all the numbers in the end? So it doesn't matter where you start. So I always start on the far left unless I have more restrictions, right? Because it might say, the end has to be a digit. So then I would start there. Okay, but I have no restrictions. So 62 times what? 62. Exactly. So 62 times 62. And if you know they're repeating, could you actually bypass this and just say? Exactly, 62 to the power 4.
Whoa.
Right? So, is that huge? Right? So 100, is it million? 14? So 14,776,336. Now the thing is, that seems like a lot, but with hackers now, is that a lot? No. Right? The computers hack so much nowadays, right? So what are most passwords asking you to do now? Put a,
Random.
like, we go to,
Oh, two-step.
right, we go to this part of the keyboard, right? We're doing like apostrophes or like stars or pound keys, right? Does that now add more of a difficulty to it? Yes. Okay. Yeah.
Why don't you do two-step authentication?
Pardon?
Why don't you use two-step authentication?
Well, exactly. But exactly. So, but that is why, but that's good. Does it make sense though now, guys, why they've actually added all this one-step or two-step identification? Yeah, because it's so easy to hack through this using computers. So even all our computers, do you guys see your teachers sometimes take their phone out and have to look at their phone and type in a... No. If you haven't, that is because we have. So if we've logged in, we don't have to do it every day, but sometimes it kicks us out because they want us to make sure that we're on our computer. So they'll kick us out and we'll have to log in. And exactly, for me, it's a text to my phone. I have to type in my code to my computer so they can guarantee it's still me. Okay. So do you guys all have your banking online? Do you have all that with at least a one-step or two-step? If you don't, set it up. You should. Okay. Right? Because and I don't have to do it every time. Right? So to me, like when I log in from this computer, I don't do it very often to my banking. But so they'll send me an email or a text saying, put the code in. Even though I put my password in, they're just making sure, did anybody get your password? Because all your personal stuff should still be connected to you. The people that are trying to hack you shouldn't have your personal stuff. And if they do, then you're really hooped. But that's what that point is for. Yeah.
You use physical keys, you just shove them in your computer and it's authenticated from using
Well, I get that, but you have to have all that set up. That's not every computer's like that yet.
I mean, true.
Huh?
It's true.
Yeah. Well, it's definitely not. But again, because you know about all that stuff, you have like every single, nobody's getting into your computer. I understand that, William. Ever. As the world gets worse, William will get smarter. Nobody's getting my money. Right? Which is good. That's smart. But not everybody's, I am not a computer whiz at all. I just know that, yeah, I try to set up my authenticator apps for all my stuff that's important, just because passwords nowadays, right, aren't very secure. But does it make sense though, the more options you have to put in a password gets it a little bit more secure for you? And that's why it's also important, if you're only using passwords, to change it often. Right? I'm the worst one for that because I'm like, yes, Sean, you were supposed to. But again, could you rotate through some passwords? You could, but you are supposed to change your passwords regularly, right? And the thing is, you guys are teenagers. Probably people that are trying to hunt for money aren't hunting you guys because you don't really have money yet, right? So think about it that way. You're probably safe right now. But as you get older, right, you might be a target. Yeah. Well, at your age, yeah, I don't know. Like they say for us, we should be changing it monthly. And the thing is, if I was more important, I might even change it weekly, right? If I was like, right. Well, I don't think he's even charged of any of his stuff that he probably wouldn't even think about it.
Unless you're like an absolute known person, like a celebrity, it's like, isn't it the same chance either way? Unless they're like keeping track.
Well,
If they try to get through all those, like, say they're hacking,
Like they change your password and the simulates your computer. It's the same chance either way.
well, it depends like if they're targeting you. So if they're targeting you and they,
Then they're keeping track.
right, so they couldn't get in, and then they're close to getting in, but then you change it, then they're starting from scratch again, right? But again, do I feel like, to me, I'm not worried about myself because if they got into my bank account, I have insurance for that, and I'm not somebody that they'd be like, oh, that was a waste of time. There's not a lot of money there, you know, kind of thing. So, like for me, meh, right? But if I was like, you know, Apple guy or whatever, and I don't know, I'm like, who has lots of money, right? Then I might be more worried. But the thing is, guys, if you have that much money, do you think they have a whole team of people watching your stuff? Yeah, right? But again, there is always, like I said, you have to be worried about identity fraud, and when you guys get Visas and MasterCards, right? That they don't get stolen, and if you do, anyway, that's a fun conversation to have as well. But right now, you guys don't have to worry, but at least you kind of get a little bit of a background. You know that 14 million, over 14 million, almost 15 million seems a lot, right? But in the big picture of nowadays, it's not really, right? When, like I said, for me or you to go and try to crack this code, would we be there forever and a day for paper pencil? Yeah, we're like, shoo-doo-doo, turning, well, really old. Yeah, so hence none of you will ever be hackers. I'm hoping you'll all stay on the up and up. Never ever. Yeah. William, do not come out of this lesson going, maybe, you know. Yeah. All right. So this is called with repetition, right? Obviously, with repetition, we have more possibilities of codes to pick. Okay, so how many passwords are possible if you're not permitted to repeat any characters? So I already heard you guys talking about that, right? So doesn't matter where you start. So again, I just like starting on the far left unless I have more restrictions. And you'll understand what I mean by that as we go through examples. I'm going to throw more restrictions at you, right? I might say it has to start with a lowercase t, right? Is that a restriction? So I would start where that restriction is telling me to go first. But here, there isn't, so I'm just going to start on the far left. So if I pick this part of my code first, I have 62. If I pick the next position, I have 61. If I pick the next position, I have 60 and 59. So 62 times 61 times 60 times 59. So obviously the number should be smaller, but still quite a few. So 13,388,280 different passcodes you could make if it was 4 digits. Your guys' banking codes, I don't want to know them, but are your guys' still 4 or are they to 6? Yours are 4? Mine's 4, but I thought I heard some went up to like 6. Some are 6? Yeah, just your PIN, like your PIN to get money out. It's still 4? Okay. Yeah. I wasn't sure if they changed that or not yet. All right. So guys, next one, this is where you have to be a little bit cautious. I would say majority of your questions are going to be rearranging random letters. Okay. So for this one it says, determine the number of distinguishable four-letter arrangements that can be formed from the letters in the word English. So here, guys, you have to think about this as Scrabble tiles. You only have an E, an N, a G, an L, an I, and a S, and a H. You have those letters and that is it. So you don't have unlimited E's. They are not going to tell you this. You have to assume by reading this you have those letters and that is it. Okay? So if I say there's no restrictions, how many four-letter arrangements can you make?
7 to 8.
Nope. Right. So how many letters in total is there? There's 1, 2, 3, 4, 5, 6, 7. So we have 7 letters. Do you guys agree that's all we have? Picture Scrabble. Have you guys know at least what Scrabble is? Right? So they're the little wooden tiles. So you have to picture. You have 7 little wooden tiles in front of you. They're right in front of me here. How many choices? Because I don't have any other restrictions. Right? I'm just making a 4-letter arrangement. Doesn't have to spell a word. Okay? I'm just making how many 4-letter arrangements can I do? So I can just start on my far left. Do you guys agree that I can put a tile there? So if I start on my far left, because I don't have any other restrictions, how many Scrabble tiles can I put there? Choices. Right. Choices for Scrabble tiles. If I start on my far left, I have 7 choices of tiles. So if I just move my way down now, how many choices do I have for letters to put in the second position? 6. Because does 1 tile have to stay? Yes. So 7 tiles are all sitting in front of me. I put 1 there. I now have 6 tiles. And then 5 and then 4. Because you're actually putting tiles. So a letter is getting in the position as soon as you go to that position. 1 gets left behind because you can't put 2 tiles in 1 position. Okay? Unless they say the E and the I have to be together. But we'll talk about that in a minute. But here, does it giving me any other restrictions other than 4-letter arrangement? So then with that, right, we're going 7 times 6 times 5 times 4. So there's 840 different ways, okay, that I can make 4-letter arrangements, okay, from the letters in the word English. Okay, so next one, I'm adding more restrictions as we go. So this one I'm saying the first letter must be a E. So it's still 4-letter arrangement. So 1, 2, 3, 4. So if this one has to be an E, that's the only thing I'm saying. The rest, I don't care which tiles they are. So the first one has to be an E. How many choices do I have for tiles in that position? 1. Now, does it matter where I go next? No. So guess where I'm going to go? Right? I'm going to just go to the tile next door. Right? So if I go right beside the 1 and do that tile next, I have 6, because I already put the E in the first position. So then I have 6 tiles to pick from for the second position. I have 5 tiles to pick for the third position. And I have 4 tiles to pick for the fourth position. So that one we can do without a calculator. So 30 times 4 is 120. Kind of making sense, guys? Kind of neat a little bit, maybe. Right, more restrictions. All right, so here it says the arrangement must contain an H. Doesn't say where. So could I technically just do one of them that contain an H and then do what? What'd you say? Times it by 4. Because is there going to be 4 different places the H can go? So you could do it once. And let's say we go back and put the H here. Right? So then it would be 1 times 6 times 5 times 4. Do you guys agree it's pretty much like what we just did? But where did I put the h? First. But did I have to put it there? I could have put it in the second, third, or fourth. So you could just do one case and times it by 4. If you hate that and can't visualize, then you have to do this. H, 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 H. You guys seeing what I'm doing? 6, 5, 4. I'll make it bigger in a second. 6, 5, 4, 6, 5, 4, 6, 5, 4. Do you guys now see what I'm talking about? That this is all the cases. Does it make sense that each case is going to be the same number? Right? So does it make sense now that you can just do one case and times it by 4 now? Do you guys see it? Because a lot of times, guys, there might be 10 cases, right? If I ask you, or in this situation, if I said use all the letters, would you have to do 7 cases? Right? Because there would be 7 positions. Okay. So to me, right, it's easier just to look at it that way. Do one case, and timesing it by 4 is just how many positions the H could have went. Right? So we count the one that it's on, but is there 3 other that it could go? Yes, so that's why we're timesing by 4 and not 3. So 30, 120, 480. So 480 different 4-letter arrangements that guarantee an H in it. All right, so first and last must be vowels. So vowel, vowel, whoopsie. So let's make sure we all understand what vowels are. Okay, so what's my first vowel in the alphabet? A, what's my next one? E, next one, next one, next one, right. So, and I know, and sometimes Y, right? So we do not include Y unless they say include Y. So we just do the A, I, O, U, and E. So no Y unless, and I've never seen them write a diploma question where they tell you to include Y as a vowel. But that would be the only way you would, okay, which like I said. So in this situation, I don't have all of them. What are the only vowels that I'm using? E and I. So I only have 2 tiles, right? I keep talking about them as tiles, not that you have to, but I only have 2 vowels, right, in this arrangement. So again, do you guys want to start on the far left or the far right? Because it doesn't matter. Left. So if I start and put my tiles on the far left, how many choices do I have if I start on my far left? 2. So if I start there, then I have to go to the end. So how many choices do I have for the far right? 1, because one of the vowels has to stay there. Right? So if it starts with an E, it's going to end with an I. But if it starts with an I, it's going to end with a E. So there's 2 choices that's going to happen for that. So then how many letters do I have left? 5. So then 5 times 4, because it doesn't matter what those letters are. Please make sure, guys, I know that we're multiplying, but do you think I have to see the multiplication symbols between? Right? There was a question on the last diploma that kids got rocked in Alberta because they didn't. Can the marker assume that you're multiplying? No. So you do actually, so I will mark like the diploma would, right? I would mark how a rubric on the diploma would mark you. So I know it's tedious, but you do have to either put the dots or the multiplication symbol in there. You can't not put that there, okay? Just because air in between, right? You can't assume multiplication symbols, okay? So put them in. I know it's kind of a little pain, but they mean something, Okay, so then that's going to equal 20 times 2 is?
20 times 2 is.
All right. Right, so with arrangements, guys, there's tons of restrictions that I can throw at you, right? You just have to deal with the restrictions as you go. Okay, so this is a common one. Sorry, go there, there. Oh, and we're not doing the whole lesson today, so no worries about that. We're only going to example 7. Yeah. That takes care of this. Right? Because this could be 2 vowels, so it could be an E or an I. Right? This, and if this is an E, that's an I. That already is taken care of here. Right? Because if you did 1 and 1, then you'd have to times it by, like if you did this as an I and that's an E, then it would be 1 and 1. But then you would have to do both cases. Right? But the 2 we started there, so it takes care of both cases. Good question. Okay. All right. So last little guy here before I show you a new notation. Okay. So here it says, in how many ways can a teacher sit 4 girls and 3 boys in a row of 7 seats if a boy must be seated at the end of each row? Okay. All right. So 1, 2, 3, 4, 5, 6, 7. So a row of 7. This has to be a boy and this has to be a boy, and they don't care what's happening in the middle. Okay. So how many choices of boys? If I have you in front of me, that I can go sit. Do you guys agree? 3 boys? So I have 3 choices of boys to sit here. Okay. And I have to make sure there's a boy in the end, so I have to ignore the middle because I have to deal with my restrictions first. So how many choices of boys do I have at the end of the row? Does it make sense that this is automatically going down by 1 as well? Because you can't have the same boy sit in the same spot. Right? So then I only have 2 choices. So that takes care of my restrictions. Now you have how many students looking at you to go into the other spots. Right? So we have 5. So we don't care what's going on in the middle. We can just position them. So I have 5 people I'm looking at. How many choices if I now go back to the left and have them sit? 5 times, 4 times, 3 times 1. And again, guys, does it make sense that once I'm done with those restrictions, it doesn't matter where I go next, right? Because it's all multiplication. So if I want, you know what, I'm going to situate a person right in the middle first, then that's where the 5 would have went, right? But it's still going to be, no matter what you do, 5 times, 4 times, 3 times, 2 times 1 in the middle, okay? So 20, 60, 120... 20, so 360, 720. Good. All right. So kind of interesting. Right? So is there a lot of ways I could arrange all of you at the water fountain outside? Right? How many of there is there right there? 2, 3, 4, 5, 6, 7, 8, 9, 10, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22. So 22 times 21 times, right, all the way down to 1 would be, if I wanted to organize you guys out at the water fountain, that would be crazy, right? How many different ways I could arrange you without any restrictions. All right, so you guys are going to learn a new notation. Some of you guys have seen it before. So do you guys do you guys agree that the water fountain example I just made up, that if I asked you, if I actually wanted to know how many different ways, right, I would have to go, I'm going to just do over here because I don't want to have to go 22 times 21 times. Are you guys okay with me? So if I was just going to arrange all of you guys at the water fountain, how many are you? There is 6 of you. Do you guys agree? So if I was just going to take you guys out to the hallway, I would go 6 times 5 times 4 times 3 times 2 times 1. So there would be 720 different ways I could line you up at that water fountain without any restrictions. Does it make sense if I start adding restrictions, guys? There's going to be less right, arrangements. So, do you guys see how I shied away from going 22 times 21 because it was going to take me forever on the calculator? Okay. There is a notation in math that will do that without having to expand it like that. Has anybody seen the factorial symbol? Okay. Yes, the exclamation, right, in math, right, is a factorial symbol, which means if you go say 22 and put the factorial exclamation, right? So if you put that on, I'll show you where it is on the calculator. It's already in here if you're reading. It will do that for you, right? You don't have to go 21, but it goes all the way down to 1. So you know how I just went 6 times 5 times 4 times 3 times 2 times 1? Okay. If you go 6, so if you hit math, this is where you find the factorial symbol. Okay. So if you hit math, right, over to probability. Okay, so over to probability. 2, 3, and 4 are what we're going to be using in this chapter. We will not be using 1 ever. Okay, but the factorial symbol number 4. So I just chose that just because I wanted to show you guys they mean the same thing. So if you don't want to have to type it all in, but remember guys, if you want to go 6 times 5 times 4, can you use this? No, it goes all the way down to a 1. Okay. That symbol in math is part of perms and coms. Okay, it gives you a nice quick way to not have to type in the whole expansion. Okay, so that's what it's talking about there. Now 0 factorial. Okay, there's a little bit of it's not a really great proof of 0 factorial, but for all of this branch of mathematics to work, 0 factorial it'll equal 1. Okay. I'm not going to explain that yet until I talk about the formula, right? And we're not going to get into the formula today. So I put it here, but we'll talk more about it tomorrow, why it's 0. Or sorry, why 0 factorial equals 1. Okay. All right, so all I'm going to do is these last 2-3 examples just to show you a little bit of well, after we do this, down here, it'll make a tiny bit more sense. But like I said, until I introduce you to the formula, you don't have to worry about 0 factorial today. Okay. But like I said, when I introduce you to the formula, you guys might have even seen it on your formula sheet already. But today is not the formula. Today is just basics. So I've only ever planned to go to chapter 7 today. So example 5, how many ways can 5 children line up at the water fountain? What are you going to say? 5 factorial. Could you still use your fundamental counting principle or permutations? Yeah, or you could write it 5 times. Right? They mean the same thing. You guys are going to notice that in this chapter, there's so many different ways, at least 2 to 4 different ways of writing things the same as we move through the chapter. So that's the only 2 ways we can write this. Right? So then that's going to be, 20, 60, 120 again. Because again, we have no restrictions. If I said there's 5 children, but little Bobby has to be at the beginning, right? Then how would I change this? It would now just be, right, 1 times 4 times 3 times 2 times 1, or 4 factorial. Okay? If I changed restrictions. Okay? So now, last little bit is, should we be able to use what our knowledge is of factorials to simplify? Because do you guys agree if I asked you to evaluate that without a calculator, without simplifying, you'd be like horrified? Yeah, I do not want you to go 10 times 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1 in your head. But I do want you to go, does anybody, exactly, all the ones that are the same, divide them out. Because do you guys agree that what's this going to equal?
10 times 9 times 8 times 6.
So what is it going to equal? 90. Do you guys all agree it's going to equal 90? So all I'd expect, guys, I don't want you to go all the way down to 1. What I want, because is that still a lot of writing if you wrote all that? What I want you to do is go, okay, 10 factorial is, yes, 10 times 9, nope, stop. 10 times 9 times 8. Can I stop wherever I want? That's where I'm going to stop. Did I get what I needed off the bottom? So don't keep going. And because I got some weird looks, guys. My Lord. Okay, let's do it. If you want to do this, then the whole point of making this easier, you eliminate it. Right? Do you see? Do I have to write all that down? You just expand the one that's bigger and expand it to where you can divide off. I don't need to keep going because is 8 factorial the same as 8 times 5 times 4 times 3 times 2 times 1? Why write it? Right? So if you want to, fill your boots if you need to do this. But what if I did 100 factorial, right, over 99 factorial? Are you guys doing this? Okay. So just expand till you can simplify, right? Because do you think I'm going to, well, you can see already. Does it make sense I'm adding variables to this puzzle? Yes, because it's the same idea. So this would just equal 90. So this, let's not do that. And again, fill your boots if you want to. But like I said, if I gave you guys 100 factorial over 99 factorial, try typing that into your calculator. Guess what it's going to do? It's going to say error, because guess what? Your calculator tries to, well, your calculator is going to try to calculate it. Is it way too big? But should you guys be able to calculate this? Yeah. Right? So that's what the diploma will do. They'll give you stuff like this that if you try to touch your calculator, it's going to kick you out because then you're not showing any understanding. So something like this would be the same as 100 times 99 factorial over 99 factorial. This just equals 100. Was that super simple? But can your calculator do it? No, you're smarter than your calculator. Okay? Because it'll try to calculate. It's a calculator. Okay? So it doesn't understand that it can simplify. Okay? To begin with. Because what it tries to do is 100 factorial. Then it goes, right? The brain explodes. So, right? That's, again, typical diploma. Stuff like that they'll do because they want to see if you understand. Okay? So then this little guy here, again, we would go 7 times, 6 times, 5 times, 4, right? Expand the larger one. It will always expand down to the smaller one. That will divide out. So then 210, right? Because 37, yeah, 30 times 7. Yep. All right, last one. Are we okay with numbers? So, before I do example 7, example 7 was included. Oh, never mind. I thought I had an example I could go back and be funny with. All right, so last one. This is super fast. Which one do you think I'm going to expand so I can make it look like the other one? Top or bottom? I heard both. Okay, so yes, it will be the top. Is the top not bigger than the bottom? Right, because the top has an n factorial. The bottom has an n minus 3 factorial. Is the top bigger? Factorial means you're going down by 1. So I can expand the top. So I start with the one I'm starting, like where it starts. So what does it start with? An n. Whoopsie. Exactly. So n. Why does it do that every time? So n times a n minus 1 times an n minus 2 times an n minus 3, stop. Right? So since we can't go all the way down to 1, the factorial stays. Did it make sense with the numbers, right, that the factorial disappeared? Right? Because again, we're going all the way down. Like if you, right, when we first wrote this, that is 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. So the factorials in this case, they cancel out now. Here, right, I didn't go down. That's why there's still a factorial on top still left. And I have an n minus 3 still with a factorial. So are those factorials going to divide out now? Yes, because an n minus 3 factorial divided by an n minus 3 factorial, they divide out. And we're left with an n squared minus n. Not that you have to expand all this, but if you, like, you could have left it, depending if how the diploma writes it, but I'm okay with you leaving it like this. Or the diploma might, because it's only 3 of them, might make you do this. So n cubed minus 2n squared minus n squared minus plus, sorry, 2n. Did I expand that right? I better double check. Dun, 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 yeah. Okay, so now, before I do the, or leave you guys with the last one, is there any restrictions? Because one is, what is n representing? What kind of number? A whole number. Exactly. So n has to be. So this one, guys, not that you really understand yet, but it can be equal to. Just because, you don't know why yet, but what did I say 0 factorial equaled? 1. So in this situation, can it be greater than or equal to? Yes. Because if you put it, because can you still not have 0 in the denominator ever? Yes. But I just told you without understanding that 3 minus 3 is 0, but 0 factorial equals 1. So is that okay that I still can put a 3 in? Yes. Okay. So it didn't ask for restrictions, but do you think you're going to have to know restrictions? So I might as well start early. Okay. So before you, right, for this expression to exist, because remember, permutations are arranging objects. We can't have negative objects. Can we have 0 objects? Yes. Okay, another little bit reason why you can have a 0 factorial. But we'll get into that tomorrow. So you guys go ahead, do this one, and then these are the questions from the textbook that match. Okay, so you don't have this written on your page because it's at the end, but these are the ones that match the first 7 examples. I'll leave it up here. But you guys, I'll leave it there, so go ahead and do this expansion. Is everybody good with the restriction being n is greater than or equal to negative 2? Did I get to ignore the top? Yes. Right, because you have to, just like we did in 20, you have to pick the restriction that satisfies both.